We'll start the session at 6:10. We'll be waiting if some people are joining. So, yeah. Okay, so we'll start the session now. So, today we are going to discuss about the week 3 lectures, right? And if you have any doubts or any questions from the last weeks, also you can ask now, as we'll start. Anyone have any question? Okay. So in the last lectures, what we studied about the surface water versus groundwater. Then we talked about what are the saturated layers, like what are the aquifers, then types of aquifers like confined aquifer, unconfined aquifers, and then other type of saturated layers like aquiclude, aquitard, aquifuse, and so on. Right? We also talked about the water balance and its components and so on. So in today's lecture, we'll talk about all the week 3 lectures and will help you in the assignment question. So with that, let's start today's session. Okay. Yeah, good evening everyone. Today we are going to discuss about the course that is Groundwater Engineering week 3 lectures. I am Balram Shah. I'm the PMRF TA for this course. I'm a PhD scholar at ICVAR at Indian Institute of Science, Bangalore. So let's start with a question. So yeah, so we ended with the types of aquifers and the types of saturated layers, and we saw there are different types of aquifers, right? Okay. So this question we have did last time, but to continue, we have started from this question. The question is, which of the following is an aquitard? Okay, just to revise, what is an aquifer? Aquifer is a formation that's sufficiently permeable to transit and yield water in usable quantities, right? So for example, the materials like sand, gravel and all, here you can see these are porous as well as it is permeable. We'll come to the term that is porosity and permeability in today's session. However, so we know that in these kind of aquifers we can yield water as much as it is available. Second one is the aquitard. What is aquitard? That which have a low permeability materials which could transmit water under vertical gradients only. Right? Then we have aquiclude, which has impermeable materials containing water but do not transmit water. So here it is impermeable. So water cannot be transmitted, but it has some water which is mostly in the periphery of the materials and so on. Finally, we have aquifuse. So the aquifers is impermeable materials which also do not contain water. So it's kind of rocks, for example, solid granite and so on. So in this case, which one is an aquitard? The correct answer is B. It is silts. Okay. Okay. So with this in mind, we'll go to the next question. The next question is, what is the term for relatively impermeable geological unit? Your options are an artesian, an aquiclude, an aquifer, and or D, none of the above. If you guys want, you can put your options in the chat box also. B, okay. Yeah, so we know what is artesian. We have talked about types of aquifer, right? So artesian came from the French word, right? And this is mostly for the confined aquifers. This is mostly for the confined aquifers. Okay. Yeah. Okay. So this is confined aquifers. And then aquiclude we have just now discussed, right? That what is aquiclude? Which has impermeable materials. However, it do not transmit water. However, it contains water. This means it can contain water in its periphery because of viscous force or because of the surface tension mostly. So it is impermeable. It cannot transmit water, but it contains water. So that is aquiclude, right? So the correct answer for this will be an aquiclude, P, right? Okay, so we'll move to the next question. The next question is, what is the difference between the saturated and unsaturated zones of groundwater? Your options are written as here. So we have talked about the saturated and unsaturated zones of groundwater, right? Just to remind you, let's say if this is the ground surface, we mostly divide it into two layers. One is the zone of aeration which we call as mostly the unsaturated zone, and second one is the zone of saturation, right? Here we discussed about three layers, soil layers and then intermediate layer, and this one will be the capillary fringe. Due to capillary fringe, there will be a capillary layer, right? And this one will be the zone of saturation, and therefore here we will have the water table. Can you give me the correct option for this? What do you think? What will be the answer? C. Okay. Anyone else? C. Okay. Okay. So here we are seeing two zones, that is the saturated zone and unsaturated zone. We know in unsaturated zone, the what and the soil layers is mostly uh, filled with both air and water, and hence it can be unsaturated zone, and therefore the pore spaces are not completely filled with water, right? Whereas in saturated zone, that is called saturated because all the void spaces are filled with water, right? So the correct answer here will be C. Here you see the pore spaces in this saturated zone are completely full of water, whereas the pore spaces in unsaturated zone are not completely full of water. So the correct answer is C. Okay. So just to revise again, because we need this in today's some of the questions. So we have talked about different kinds of aquifers, right? One is the unconfined aquifer, which has the atmospheric pressure mostly at the water table. Then we have confined aquifer, which we also call as pressure aquifer, right? So here you see in this what we are seeing, this one is the ground surface, for example. Now in ground surface we are putting three wells, right? Now you see the first one, that is this water table well, we call unconfined aquifer as water table aquifer also, right? So here we'll have till water table we will have the water, right? That is unconfined aquifer. If you put in the confined aquifer, you will see that when the piezometric head, or we can you see this line? This line we are calling as piezometric surface, right? So if the water table is below the piezometric surface, then what is firstly what is confined aquifer? That it is sandwiched between two impermeable layers, right? Because of which there is pressure created in the water, and hence that we call as pressure aquifer. So if the piezometric surface is above the water table, then what will happen? The pressure will again try to balance the atmospheric pressure, and it will stay within the well. However, if here you see here, in case of this, let's say if we call it as well 3, if the piezometric surface is above the water table, what is happening, or above the surface, ground surface, then what is happening? There is flow of the water happening directly due to the pressure from the confined aquifer. So here, for let's say for well 2, piezometric surface is lower than the ground surface. This we call as ground surface. Whereas in well 3, what is happening? Our piezometric surface is above the groundwater surface. This is above the ground surface, and hence there is a flowing well, because of which we are calling it as artesian well. Okay, so there can be recharge. That's why we have recharge area, and below this, whatever strata are there, we are considering that as impermeable strata. Okay, any questions here? Okay, if not, we'll move to the next question. Okay, so this is a simple question. Here we have talked about hydrological cycle, right? There we talked about its component like precipitation, evapotranspiration, runoff, and so on. So this is related to precipitation rainfall only. The question is, the diagram below represents a cross section through a coastal mountain range. Okay, so we have ocean here, right? And then at the coast we have mountain range. Okay, and then again we have planes after that. Okay, I hope you can visualize this. Which of the following statement is correct? So we have wind flowing in towards the mountain. Let's say the leeward direction is the B, the windward direction is A, and towards plane we call it as C. Now, can you tell me which side will receive the most precipitation, or whether all the sides will receive equal amount of precipitation? A, okay. Also, if any of the, let's say A, B, or C is receiving highest amount of rainfall, can you give me the reason why you think that it would receive the most precipitation? Okay, so let's say this is the ocean, right? But what is the direction of precipitation? Okay, okay. Let's consider that whatever water is coming, it is coming most whenever we start from the water cycle, we mostly start at the ocean when we are at the coastal region, right? So most of the water which will come in this direction. So because we are saying wind is coming from this direction, mountain block the water getting wind. Yeah, I'll come to that. So due to the sun radiation or solar irradiance, what will happen from ocean? We'll have the evapotranspiration, and we know because of the evapotranspiration, water vapor will come up, and due to the convection, the clouds will form, and it will move now in this direction. Okay, so that's why ocean we have mentioned here. Now the wind is taking those water vapors in the form of clouds. What will happen? Because of this barrier here at A, there is a big barrier. So there is a big mountain, for example, because of which the this layer will block this wind, and because of which the wind again will go back. Some of the winds which is carrying the clouds above the mountain, it can be possible that, let's say, if 4000 meter above the mean sea level we have mountain, but above that also water vapor can move, right? So some of the wind can take the clouds in this direction also, right? But it will be again some part because of the mountain, there will be rainfall in this direction, which we call as orographic rainfall due to the mountain, right? So most of the water or most of the precipitation which will happen at this windward side of the mountain, that is E, and remaining will happen in B or C. We are considering that there is no water vapor coming from the land direction. That's why we have mentioned here ocean. Okay. Any question here? So the correct answer is region A will receive the most precipitation. If you have any question, you can raise your hand or you can put in the. Okay, I hope this is clear. So we'll move to the next question. The correct answer for this is A. Okay, okay. So the next question is flowing artesian wells are expected in areas where your options are: the water table is very close to the land surface, the aquifer is confined, the elevation of the piezometric headline is above the elevation of the ground surface, and D, the rainfall is intense. Any guesses? See, okay. Just now we have seen this, or I have explained this. So what do we mean by flowing artesian wells? We just saw one diagram here. So here you see, I said that this we can call as piezometric surface or piezometric line. Okay. So if the piezometric surface is above the ground surface, this is the ground surface, right? Then what is happening? This pressure water is coming and it is flowing above the ground. Okay, and that's why here we can see the elevation of the piezometric headline is above the elevation of the ground surface, and that's how the flowing artesian wells are expected in those areas. Okay, so the correct answer is C. Fine. We'll move to the next question. Okay, so moving on to the porosity. First, let me explain a little and then we'll move. Okay, so one of the important characteristic or index property of the soil materials or the subsurface layer is the porosity. Okay, now let's suppose you consider one layer. Okay, in that there will be materials or soil materials, let's say the soil or rock, whatever you consider, right? So you see here we have seen earlier also that there are different voids, or we call that as interstices, right? There can be different voids or interstices. So, or pores we also call it, right? So what is porosity? Porosity can be written as the ratio of the volume of voids to the total volume. Total volume as in the total volume of the layer, if you can consider. Okay, so porosity is defined as the ratio of volume of void spaces in a rock or in a sediment to the total volume of the rock. Total volume of soil. Okay, so this one will give you in decimals, right? This porosity is also expressed in percentage. Okay, so you can write N as VV. Here I am calling VV as the volume of voids, and total volume I am calling as capital V. Okay, so into 100. So if you just multiply it by 100, you will get in percentage. Okay. Okay. Now, let's say if you don't have volume, you can express this in the form of density also. So you see here, you can write the porosity as volume of voids, which is nothing but the total volume minus the volume of solids, right? So in this layer, let's say, finish writing. Yeah. So in this layer, if you consider in the top, which I have drawn here, we have two things. First one is the soil particles, right? And the other one are the voids. So total volume will be consisting of, so total volume V will be consisting of volume of voids plus volume of solids, right? Do you agree with this? Volume of voids can again have both. Volume of voids can have both volume of water and volume of air. Okay, for now we are just saying the total volume will be consisting of volume of voids and volume of solids. Okay, so we can write what if we can write if this is correct, then we can write volume of voids as total volume minus volume of solids. Right, so you can write this as 1 minus volume of solids, or maybe I'll write it in simple form. Sorry. Okay, so we can write this as 1 minus Vs by capital V. Now, if you want to change this in the density form, you can write what is volume of solids. Volume of solid, we know mass equals to density equals to mass by volume. This is density. Okay, so there will be some density of the materials or density of soil, and if you consider the whole density of the layer, then we call that as bulk density, or I am writing it as rho bulk. Okay. Okay. So we can write the volume of solid as mass of solid divided by the density of solid, right? Into what is the total volume? Total volume can again be written as mass of the total layer, or what will be the mass of the total layer here? Can you tell me? Mass of the total layer will be equal to the mass of solids, because mass will give you how much due to gravity it is there, right? So we are considering that air does not have any mass here, so we can write this as mass of solid divided by density or bulk density. So we can write this as bulk density divided by the density of the solid. So you can write uh, porosity in volume units, or you can write it in the form of density. Okay, is this clear? Then we'll move to the question. Okay, so we'll move to the question then. Okay, so the question is, the porosity which considers the amount of interconnected pore spaces available for fluid flow is called. Okay, so for this we need this little more. Okay, so now we understand what is porosity, right? So can you tell me the factors that affects porosity? Anyone? What do you think are the factors? Just you can just think basic things. Okay. In porosity, what two things are there? Firstly, we have the solid materials and the void. Okay, and in which water can flow. So whatever fluid we will talk about in this course, as we are talking about groundwater engineering, we will talk about water as the fluid. Okay. Okay. So what are the factors which you think can affect the porosity? Firstly, the grain size. So if we know that if the size are bigger, it can be possible that the voids gets bigger. Okay, and then again shape of the grains. If the shape of the grains are rounded, then what will happen? If you see this is shape of the grains or the shape of the solid materials, whatever you can say. So let's say if sediments or whatever grains you are considering are well rounded, then what will happen? It will have higher porosity than any fine grained sediments, right? Because the grains will not fit together in case of the well rounded coarse grained sediments. Okay, then degree of sorting. If the grains are not sorted well, then it might be possible that the porosity is more, because the void spaces can be more. However, let's say if as a human we are putting some bricks, then what we'll do, we'll mostly put it in sorted order, right? So if it is properly sorted, then it will have less porosity in it. And then also degree of cementation. So if cementitious materials are there, then it might be possible that the porosity will be less. Okay. Okay. Now next we will move to the types of porosity. Okay. Generally, there will be three types of porosity. First one is the primary porosity. Second is the secondary porosity. And third one is the effective porosity. Okay, so what is primary porosity? Primary porosity is, let's say, during the beginning of the rock formation, or let's say whenever the rock formation was done. So that original porosity of the rock when it was formed, we call that as primary porosity. Okay, so porosity at time of rock formation. Then what is secondary porosity? So later, let's say now rock formation has happened, and due to weathering or due to fractures in the rock, there will be porosity can change. So it develops due to fracture and or weathering later on. Okay, and third one is effective porosity. What is effective porosity? Now let's say we know, let's say in this layer, okay. So you see, if you consider this layer here, there are so much of voids. If let's say water is flowing from vertically, then what will happen? It will seep through this. It can go like this, and then in this way it can go, right? But when it comes here, it can be possible that at this place, the water is only contained, and it cannot transmit. So the amount of interconnected pore spaces which are available for fluid flow, so whatever other void spaces you can see there, the fluid flow or the water flow can happen, and that porosity, only that volume of voids will be considered into the porosity, and then we will call that as effective porosity. So what is effective porosity? The effective porosity is the amount of interconnected pore spaces which are available for the flow of water, which is also again expressed as the ratio of voids to the total volume. Okay, so again we can write this as effective porosity as volume of voids by the total volume into 100 if you want to see in percentage. However, this volume of voids will be interconnected so that water can flow. Okay, so mostly we considered in the layer that the volume of voids are mostly interconnected. However, in case of let's say acute or something, then we see whether it is interconnected or not. Okay, so what is porosity? What porosity gives you physically? What is the physical meaning of porosity? The physical meaning is like porosity will give you a measure of how much water can be stored in that geological material. Okay, okay, okay. So we'll move to the question then. Till then, till here, do you guys have any question? Okay, if not, we'll move to the question. Okay, so the question is the porosity which considers the amount of interconnected pore spaces available for fluid flow is called primary porosity, secondary porosity, effective porosity, or negligible porosity. C. Okay, anyone else? Hmm. Yeah, just now we have discussed, right? So the correct answer is effective porosity. C. Okay, just a small number crunch. A soil sample has volume of voids that is zero point 0.4 liters and volume of solids as 0.76 liter. Determine the porosity. Can you just do this for me? I'll wait for 2-3 minutes. Let me know how much you are getting. Okay, anyone got any answer or anything? Okay, maybe I'll do that. Okay, so let's say I'm calling volume of, no, you guys are doing, should I wait or, okay, maybe 1 2 minutes to take more. Wait. Okay, I'll do that. Okay, so let's consider the volume of voids I'm writing as VV and volume of solids I'm writing as VS. Okay, so we know porosity, or we are writing porosity as N. Okay, so porosity is can be written as volume of voids by total volume, right? And we know this can again be represented as, just now I told that total volume we can write as volume of voids plus volume of solids, right? So in this we don't have to do much. So we know volume of voids is zero point 0.4, and volume of voids is again zero point 0.4 plus 0.76. How much I'm getting? Let me check. So I'm getting somewhere around 0.3448. Okay, so let's say here I'm putting it in percentage. Okay, so we can multiply this by 100. So n in percentage we can write it as 0.3448 into 100, that is around 34.48%, right? Yeah, so I took decimal places less, that's why it is near. So the nearest one is 34.64. Okay, so the correct answer is 34.64%. Is it clear? Or if you have any doubt, you can ask. You can switch on the audio also if it is fine. So the correct answer is B. Clear, right? Okay, so we'll move to the next part. Okay, so for this, again, we need. mm, Okay, so now we are done with porosity. Next, we will talk about surface runoff, or not only surface runoff, the total runoff. What is runoff? We talked about hydrological cycle and its component, right? And we wrote, let's say majorly if you write, we write it as precipitation equals evapotranspiration plus runoff, or Q, plus or plus minus change in storage, that is TSDT, right? If you just consider the major components. Now here, this runoff which we are calling for a catchment, let's say if this is a catchment, mostly the streams that you can see, if you measure only the flow in the streams, most of the books they write it as stream flow. Okay. However, if you consider all the water that is running off from the catchment, we call that as runoff, including the base flow. So, what I'm meaning by that, let's say this is the catchment, okay, and this is the ground surface. So, this is the catchment, something like that. And let's say if precipitation is coming, the water is flowing in the streams, and not only in the streams, it will infiltrate and percolate, right? And later it will also flow as groundwater, right? So let's say at the outlet, what you will get this groundwater as base flow. So this one will act as base flow, and this one will act as stream flow. Okay, so the total runoff will be what? Total runoff will be stream flow plus base flow. However, in most of the studies, you will see that we use stream flow and runoff equivalently. Okay, but there is a small difference between that. Fine. So now we know what is runoff, right? Now here we saw that base flow is coming and joining the river. So like that, we can divide the streams into two. First one is the influent stream and second one is the effluent stream. What do we mean by that? Okay, maybe we'll draw and we'll understand. So let's say this is the ground surface somewhere. Okay, so let's say this is the ground surface. Okay, and water table is somewhere below here. Okay, so what will happen? Let's say if this is the stream, water is there, the water will infiltrate and percolate and it will again reach or join the water table here. This is the water table, right? So here what is happening? The stream or the reach of the stream is losing water to the ground and contributes water to the saturated zone, right? So here we are seeing the water is flowing into the water table and hence we call that as influent stream. Similarly, let's say if this is our here we have stream, okay. However, the water table is somewhere here only. Okay, so we have water table here. So here what is happening from the from the saturated layer, the water is going inside the stream. So therefore, a stream which is fed directly by the groundwater or the piezometric surface and is above the base of the stream, we call that as effluent stream. Okay, so in influent stream, water is getting inside the water table. Okay, from the stream. However, in effluent stream, from the water table, it is getting out. That's why we are calling that as effluent stream. Okay, so think you put in the beginning the water table, how from water table the water is flowing. If it is coming in the water table, we call that as influent. If it is going out from the water table, we call that as effluent stream. Okay, so influent stream is the runoff or the, let's say, stream flow is the water that is discharged through the streams consisting wholly or let's say in part of water contributed by overland flow and the groundwater flow, that is base flow. Whereas in effluent stream, it let's say impervious horizons are there, which is above the water table. Then at the land surface, water will flow through them to reach the stream as interflow. So here this we call as interflow. Okay, is it clear here? Okay, so there are different factors which affects the runoff. What all factors can be there? This you guys have anyway explained nicely in the lectures. Just I will just name all those factors. Firstly, let's say the size and shape of the drainage basins. Here we saw that the drainage basin can be fan shaped, right? It can be fern shaped and there can be different shapes. So it also, so if there is a uniform precipitation, for example let's say 100 mm, because the area of this is more, it can be possible the runoff will be more, whereas the area is less, so the runoff can be less. So it depends on the area of the basin, it depends on the shape of the basin, it depends on the size of the basin. So basically it depends on the dimensions and the configuration of the drainage basin. It also depends on the climate change. So let's say if there is some climate change is happening, which we know all over the globe it is happening. So the precipitation has increased, or let's say the duration has increased. In some places you will see the precipitation duration has decreased. The aerial distribution of precipitation has changed. The rainfall intensity has changed. So based on all these conditions, let's say evapotranspiration has increased or some other factors, let's say temperature has increased because of which the evapotranspiration is getting more. Because of this, the surface runoff will get affected. Again, the moisture content of the soil. So let's say if the soil is saturated, then what will happen? Whatever precipitation will come, it will mostly flow as the surface runoff, right? Yes, last week we have talked about the infiltration, and if rainfall intensity is more and if infiltration rate is less, what will happen? Those things we have discussed. Then it also depends on the topography and land surface slopes. So we know if the land surface slope is very steep, what will happen? The runoff will go very fast and we'll have less runoff on the surface there. Okay, it also depends on infiltration and permeability characteristics of the soils and subsurface formation, what kind of aquifer is there or what kind of saturated layer is there. Then also one of the important in nowadays is human activities. Okay, so let's say we are changing land use, we are changing maybe agricultural land to, let's say, urban land. Then what will happen in urban land? We are mostly doing concreting and all, right? Because of which the whatever infiltration would have happened before is not happening, and hence the surface runoff is getting more. Okay, so like that, if you change the land use, or let's say if you're doing urbanization, if you're doing diversion of water, if you are constructing some dam, so you are storing water for some time, right? And hence in the downstream side, it might be possible that the surface runoff will be less. Okay, so these are some of the factors on which the runoff depends. Okay, okay. So we have different kind of flows. We have infiltration, excess overland flow. This we have talked last time, right? That I talked about the rainfall intensity, then infiltration capacity, right? FC, and then infiltration rate, FT. This we have talked last time, that's why I'm just going fast. So we know that let's say if the rainfall intensity or the rate of rainfall on the surface exceeds the rate at which the water can infiltrate, that is I is greater than FT, then what will be the infiltration rate? We have talked about this last class, right? If the rainfall intensity is more than the infiltration capacity, then the infiltration rate, sorry, infiltration capacity. Oh, sorry, infiltration rate only. So infiltration rate will be equals to infiltration capacity, correct? Right? Similarly, if rainfall intensity is less than the if the rainfall intensity is less than the infiltration rate, then the infiltration rate will be equal to the rainfall intensity, right? So because of this, let's say due to precipitation depression, storage has also filled. Then whatever excess flooding or excess flow is happening on the surface, we call that as flooding excess overland flow, or Hortonian overland flow, or unsaturated overland flow. Okay, so mostly this is seen in arid or semi-arid regions, right? Okay, and the next one is the saturation excess overland flow. It is like whenever the soil is saturated and the depression storage are filled and still rainfall is going on, then what will happen? This rainfall will immediately produce surface runoff. As I said that, let's say if there is some antecedent soil moisture. What do you mean by antecedent soil moisture? That from uh, before the rainfall event, we have the soil moisture saturated, for example. Okay, so after water infiltrates the soil on an upslope portion of the hill, the water will flow laterally through the soil and it will exfiltrate. So it will flow out of the soil and it will be near the channel. So let's say this flow is called subsurface flow, or let's say through flow. So let's say if the soil is saturated, then what will happen? The whatever water will come, it cannot infiltrate, and hence it will flow as surface runoff. This we call as saturated overland flow or saturation excess overland flow, or let's say dune runoff. Okay, okay. So till this everything is clear, right? We'll move to the question then. So the question is, a stream that provides water to the water table is termed as, just now we have discussed this, D, effluent streams. So here you see here what we are saying. Sorry. Let's say there is some stream. So this is the cross section, okay, not the top view. So this is the stream, and what it is saying, the stream is providing water to the water table. So let's say somewhere here the water table is there, and this stream is providing water to the water table. We call this stream as, what do we call this stream? Just now we have discussed, right? Someone said D, right? No. Okay. So the correct answer is influent, because as I told you, just to keep in mind, how will you remember? If it is coming inside the water table, we call that as influent. If it is going out from the water table, we call as it effluent. Okay. So the correct answer is B. It is influent. Okay. Okay. Fine. Good. Okay. So the next question is the flow occurring when the rate of rainfall, let's say I, on a surface exceeds the rate at which the water can infiltrate, that is FT, the ground, and any depression in storage has already been filled, is called what kind of flow? B, that is saturated overland flow. Okay. For saturated overland flow, firstly, there should be the soil should be saturated. Here we are only saying that rate of rainfall is exceeding the infiltration rate. However, the soil is not saturated, we are not seeing here. So in that case, firstly, what will happen? The rainfall will infiltrate towards the to the ground. Okay, so I will be F FT will be equals to FC, right? Just now we have discussed here. What is that? Right? FT will be equals to, it's not coming. FT will be equals to FC, right? So wait a minute. Okay. So the correct answer for this question will be Hortonian overland flow, or we call that as flooding excess overland flow or unsaturated overland flow. So when the soil will be saturated and then the depression storage is filled and still the rainfall is continuing, then whatever runoff will be happening, that we call as saturated overland flow or Dunne runoff. Okay, is it clear? Okay, so we'll move to the next question. So the next question is related to Darcy's law. Okay, so before that, maybe we'll discuss about Darcy's law first, and then we'll come to this. Okay, so now we are moving from stored water, or let's say how water behaves, to movement of water. So mostly we talk about movement of water now. Okay. Okay. So, what is Darcy's law? Firstly, Darcy's law was given by Henry Darcy long back in 19th century, in which they did a series of experiments. Okay, I think I should have the picture here. Let me check. Here it is. Okay, fine. So it was given by Henry Darcy in 19th century. Okay, and what he did a series of experiments. So it was a field experiment kind of. So it was not a lab experiment. So what he did in the picture we can understand properly. So for now, let's consider that this is a pipe, for example. Okay. However, he did on a field, and what he did, he put two manometers, one, let's say, for example, at the top of the mountain, and one at the end of the mountain, for example. Okay, so these two, whatever you can see, are the manometers, for example. Okay, so now you see, uh, because we are going below, so what will happen? We know that water will flow from high potential to low potential, or if there is a slope, it will go from up slope to down slope, right? So let us consider that del L here as the length of the or let's say if we consider this point as x, this point as y, then we call del L as the distance between the x and y, that is measured along the direction of flow. So here you see Q we are saying as the flow or discharge or flow. of water. Now the direction of flow is in which direction? From x towards y direction. Okay, so L or del L is measured along the direction of flow. Whereas because of the potential gradient, we have del H, which we call as head loss. Why this head loss is happening? Because in the top there is high potential energy, and in the down it is low potential energy, and there is head loss, and that is what we call as del H here we are calling. Okay, so let's say if you consider the cross sectional area as capital A. Okay, then according to mm, Darcy's law, what we can write, that the flow or the discharge is proportional to, firstly proportional to area, that is A, or cross section area. The discharge is proportional to the head loss, and discharge is inversely proportional to 1 by the length. Okay, so from these we can write Q is proportional to A into del H by del L. Okay, and this term we call as hydraulic gradient. Hydraulic gradient, right? Which we directly or mostly denote by I. Okay, so now I'll write here Q equals, or Q is proportional to A into del H by del L. Okay, now for if we want to change this proportionality to equal or equation, we have to put a proportionality constant, right? So let's put K as a proportionality constant. This K, as we are writing, this is a proportionality constant, right? Okay, and this one, if you see physically, we call this as hydraulic conductivity. What is hydraulic conductivity? From the word conductivity, do you understand anything? Just from the word, no need to think of groundwater engineering or something. In electrical or also something in physics or something you have studied in your schools, right? Electricity conducts conductivity. You might have studied, right? Yeah, water flow easily. Yeah, so what is hydraulic conductivity? Hydraulic conductivity will explain that how easily the water will flow from the porous media. Okay, so it will give you the ease of water flow through porous media. Okay, so here you note two terms. First one is the water flow. Second one is the porous media. Right? Why I am asking you to note here? Because we'll see something just now. Okay, so in hydraulic conductivity, we are saying that it is the ease or how easily the water can flow through the porous medium or through the pore spaces that is there, which are interconnected, for example. Right? So hydraulic conductivity, or K, is now a function of the fluid as well as the material, or the porous material, for example, right? So this hydraulic conductivity, if it is independent of the fluid, so if you remove, or if you remove the effect of the fluid, then we call that as intrinsic permeability or the coefficient of permeability. Okay, so yeah, talk about that. So here we are seeing that K is a function of both fluid properties as well as the porous material properties, right? So now if you remove the fluid properties, then we call that as, or only the function of porous material properties, we call this as intrinsic permeability. So intrinsic permeability is only due to the materials of the porous medium. Okay, so we call this as intrinsic permeability, or let's say coefficient of permeability. So many of the places, many of the studies, you will see that we use the hydraulic conductivity and the coefficient of permeability very much equivalently. However, there is a small difference. But let's say if the effect of fluid is not substantial, then we can consider the hydraulic conductivity or the coefficient of permeability as equal. Okay, and that's how in many of the cases, not in the real life scenario, in one of the problems or many of the theoretical things, you will see that we consider the hydraulic conductivity and coefficient of permeability as same. So just note that for, okay, I didn't write, this is hydraulic conductivity. So this one is hydraulic conductivity. Okay, so the units, if you see for the hydraulic conductivity, what will be the unit? You can just use this equation of Darcy's law, and you can tell me. Anyone? What is the unit of hydraulic conductivity? Q by area. Yeah, so Q by area is what? Q is in meter cube per second, let's say, and area is in meter square. So it will be what? Meter per second, right? So the unit for hydraulic conductivity will be meter per second. Okay, just okay. So you can write this as Q. So Q equals, and because the flow is going in downward direction, sometimes in some books you will see there is a negative sign. Okay, that negative sign is because of the downward movement. Okay, so K into A into I. I am saying as hydraulic gradient. Okay, okay, yeah. So unit of hydraulic conductivity we saw that it is. So if you just see the dimensions, we'll go one by one so that it is easy for you. What will be the dimension of Q? Q will be meter cube per second, right? So we can write L cube t to the power minus 1. So here we know the fundamental dimensions are length, time, and mass. Okay, so here we don't have any mass, so the dimensions for Q is meter cube per second, that is L cube t to the power minus 1. Hydraulic conductivity we saw it is meter per second, and hence it will be L to the power minus 1. Okay, and again if you see the unit of intrinsic permeability, that is small k, then what will be the unit of uh, intrinsic permeability? It will be meter square. So the dimension will be L square. Okay, so yeah, so we talked about intrinsic permeability, we talked about hydraulic conductivity. Again, now this hydraulic conductive or this hydraulic conductivity will be affected by, as we know, both porous mediums materials property as well as the fluid property. Okay, so if you see hydraulic conductivity or K, let's say at different temperature, it will be different, right? Because if temperature will be there, we know that water will have an different property. So we can write this as this formula. Okay, so what is new? New is the unit weight, or not unit weight, it will be kinematic viscosity. Kinematic viscosity of water. Okay, so L here represents the laboratory, and T says the temperature. Okay, or let's say standard temperature. Okay, so now you just I'll give one case. Let's say if the temperature is increasing, then what will happen to the kinematic viscosity of water? temperature is increasing, what will happen to the viscosity of water? Will it become more viscous or will it become less viscous? Anyone? Viscosity we know, right? So if temperature is increasing, the molecules in that fluid, it will have more kinetic energy and hence it will have less viscosity, right? So if it has less viscosity, so if temperature increases, then what will happen to the hydraulic conductivity at some temperature? If temperature is increasing, then what will happen to the hydraulic conductivity? It will decrease, right? Should it be? So you see just the equation. You see, if the temperature is increasing, this factor will reduce. And if this factor is reducing, what will happen to the hydraulic conductivity? It should increase, right? Yeah, it's clear, right? Okay. Okay. So mostly standard temperature is considered near 60 degree Fahrenheit, where you consider this as 1 at 60 degree Fahrenheit. Okay. So just let's say if some different temperature is there, you use the conversion factor for delta T or nu T, which we are calling here. Okay. Yeah. So how do you get this hydraulic conductivity? So there are different determination procedure, or how do you determine? I'll just name those because that will not be there. So there are several empirical formula that researchers or the scientists have formulations have created to get the hydraulic conductivity. Okay. Then there are different lab tests you might have done if anyone has done maybe geotechnical things and all. So we use permeameter, that is constant head permeameter, or variable head or falling head permeameter. We also say it as variable head permeameter. So we use permeameter to calculate the hydraulic conductivity. Okay. Then we also use tracer test. There are different tests we can do to determine the hydraulic conductivity. We can use auger boring or auger hole tests. And then we can also do pumping test of wells. Okay, so these are some of the determination. How do we determine the hydraulic conductivity? Fine. So till this, everything is clear. If everything is clear, we'll directly move to the questions. Yes. Okay. Okay. One more thing I have to say that outside internet. Okay. So yeah. So for any law to be applicable, there will be several assumptions in those law. Let's say something like that. So Darcy's law is valid only for laminar flow, not for turbulent flow. It is applicable for both steady and unsteady state equation. If you use one more equation to the Darcy's law, so I'm not writing steady state and all. So it is mostly applicable for laminar flow. Okay. So what is laminar flow and all we'll discuss in the next class. Just to note. So laminar flow. If a flow is laminar flow or turbulent flow and all, we generally used Reynolds number. So maybe it is not explained, but just to know what is Reynolds number. The Reynolds number is a ratio of inertial force to the viscous force. Okay. So if the viscous force is high, then what will happen? The Reynolds number will be less. So whenever the Reynolds number is less than 1, we call that as laminar flow. Again, in some books you will see different values. Okay, in some books you will see Reynolds number less than 2000. In some books you will say Reynolds number less than 1. It depends on what kind of units you are using. So just be cautious with the units. Okay, so for now we will just see that if Reynolds number is less than 1, we call that as laminar flow. So therefore the Darcy's law will be applicable when the Reynolds number will be less than 1. However, the upper limit can be extended to Reynolds number somewhere near the 10. Okay. 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 So we have the Darcy's equation, Q equals to minus K into A into dH dl, or whatever we have used before. So this one will give you what? This one will give you the total discharge. However, you can also calculate different properties, for example, or not properties, different fluxes, you can say. So small q or specific discharge, how do you go for from the flow to flux? You just divide it by area. So this you write as capital Q by A. So we can write it as Q into dH, or maybe I'll write dl del H only because we're using del H, right? Del H del L to del H del L. Okay, so this one is the specific discharge. You can also calculate the velocity. Velocity will be given as minus K by effective porosity into del H by del L. This is seepage velocity. There is a small difference between the seepage velocity and the actual or the discharge velocity, but for now you just note that this seepage velocity we are talking about. Okay. Okay. So till this everything is clear. Then we'll move to the question answers. Or else maybe, yeah, okay, fine. So we'll move to the question. Next question is, Darcy's law is not applicable for steady flow, turbulent flow, laminar flow, and flow with Reynolds number less than 1. Yeah, so we know that it is applicable for steady flow. Steady and unsteady flow are mostly, if the properties of the flow is not changing with time, we call it as flow as steady flow. Okay, so these kind different classifications of flow anyway we'll discuss in the later sessions. So Darcy's law is not applicable for turbulent flow, but it is applicable for other three. Okay, so the correct answer is B. Okay, moving to the next question. For the same soil or material, if the hydraulic head loss, let's say del H here, is reduced to half and the cross-sectional area A is doubled and the flow length L remains unchanged, then the discharge Q will be. Your options are this. Can anyone tell me what? What would be the answer? A, okay. Just to note that we know that Q is proportional to A into del H by del L. Okay. So let's say if you write it as Q1 equals to K into A1 into del H1 by del L1, you have to find out what discharge Q2 will be, or what is the relation between Q2 to Q. So Q2 hydraulic conductivity will be same, right? The area is doubled, so it will become 2A or 2A1 here I am writing into what happened to hydraulic head loss, it became half, so it can be written as del H1 by 2, and the flow remains same, that is del L. Okay, so you can see it becomes 2 into A1 to del H1 by del L1 into 1 by 2. This 2 will cancel out, and we can write this as K into A1 into del H1 by del L1. That is again equal to Q1. Okay, so as Q2 is equals to Q1, what is happening to discharge? It is remaining unchanged. Okay, so that this is clear. Yeah. So if you have any question anytime, you can just ask me. Okay. Okay. So the correct answer is A. Next question is again a small difference, maybe no. Okay. The question is the permeability of a soil sample at the standard temperature of 20 degrees Celsius was 0.01 centimeter per second. Now, the permeability of the same material at a flow temperature of 10 degrees Celsius in centimeter per second will be, we have discussed this, right? Anyone? So here what is happening? The temperature is reducing. If temperature is reducing, then what will happen to the viscosity? The viscosity will increase, correct? And we know the formula Kt is equals to K into kinematic at laboratory divided by at that temperature. Now, if this is increasing, then what will happen to the permeability? The permeability should decrease, correct? So the correct answer will be less than 0.01 degrees Celsius. Is it clear? Are you guys with me now? Okay, so the correct answer is A. Any questions? Anamika, Chetan, Mohammed Shafiullah, anyone? Okay, all right. Okay, so we'll move to the next question then. The unit of intrinsic permeability is B. Okay, anyone else? Just note that here I am talking about intrinsic permeability. So intrinsic permeability is only dependent on or is a function of the material property, or let's say whatever soil material property. So it is independent of any fluid property. Okay, and we just now we have seen that the unit of intrinsic permeability I have wrote before, I guess. Let's see. Yeah, here I have written that for intrinsic permeability the unit will be in area unit, that is meter square. Okay, so the correct answer will be some area unit, whatever area unit it is. Yeah, so now what will be the unit of intrinsic permeability? It will be B, that is centimeter square. Okay, yeah. Okay, we'll move to the next question. The next question is a small number crunch, a small problem. Maybe you guys can do it with me. First you guys do, then we'll discuss. So the question is a sand sample of 35 centimeter square cross sectional area. So we have area is equals to 35 centimeter square. Okay. 20 centimeter long, we'll write L as 20 centimeter, was tested in a constant head permeometer. Okay. Now under a head of 60 meter, H equals to 60 meter, 60 centimeter, sorry. The discharge was 120 ml milliliter in 6 minutes. So T is equals to 6 minutes. Also the dry weight of the sand used for the test was given as 1120 meter. So we'll write dry weight as 1120 grams. Determine the hydraulic conductivity in centimeter per second. Can you guys do this for me? Maybe I'll give you 5 minutes. It will take some calculation. So I'll give you 5 minutes. You guys do, and then I'll do if you guys don't get it. B, okay. Okay, maybe then I'll also do. So first maybe I'll convert Q in from milliliter to meter cube or centimeter cube. So we know 1 liter, 1 meter cube is 1000 liter, right? And 1 meter cube is 10 to the power 2. So 10 to the power 6 centimeter cube is 10 to the power 3 liters, or this can be written as 1000. So okay, 10 to the power 6 milliliter. So we can write 1 centimeter cube as 1 milliliter then. So we can write this in the 120 centimeter cube, right? Okay. And now we know, as per Darcy's law, Q equals to K into A into H by L here, because I have written H and L. Okay. So now we have Q as 120 centimeter cube. K we have to find out. A is 35 centimeter square, and H is 20 centimeter, and sorry, H is 60 centimeter. H is 60 centimeter, L is 20 centimeter, right? You just need to find the per second. Oh, okay. The discharge was 120 ml in 6 minutes. So it is in 6 minutes. You have to convert in seconds also, right? So divided by 6 into 60 seconds. Okay. Now you just calculate K. I'll just do the calculation one. Let me do it. Yeah, so it is coming somewhere near 0.003176 centimeter per second, right? This can be written as 3.174 into 10 to the power minus 3 centimeter per second. So you are right, correct. So the correct answer is B, that is 3.174 into 10 to the power minus 3 centimeter per second. Okay. Okay. So any question in this? Any doubt? Okay, if not, we'll move to the next question then. Okay, so the next question is the rate at which water passes through a unit width of the aquifer under a unit hydraulic gradient is termed as. We didn't discuss this, just to note. A, right? A, that is hydraulic conductivity. Just note that we are talking about passing through a unit width. So hydraulic conductivity is what? Is the rate of flow under unit hydraulic gradient through unit cross section area, that is A, of the aquifer. Whereas transmittivity is the rate of flow under unit width. Okay, so the correct answer will be T, and we write this T as K into B, where B is the width of the aquifer, let's say. Okay, so the correct answer will be transmissivity here. Okay, that is B. Okay, we'll move to the next question then. Next question is water that is good enough to drink is called. This is a simple question. A, that is potable water, right? Correct answer is A. Next question which we have is when the soil zone becomes saturated, water dash downward. Water will percolate downward, right? So the correct answer is C. Okay. Yeah, correct. Nice. So with that, we will end. In the end, we have also discussed about the classification of flow in the lectures, right? However, we have a detailed discussion of this classification of flow. Just to note that what are the classification of flow, I'll just mention those. However, we'll discuss in detail in the next session. Steady and unsteady flow, which we know that it depends on the time. So if with time there is no change in flow or the flow properties, then we call it as steady, otherwise it is unsteady. Then we have laminar flow and turbulent flow. We also have transition flow. We'll see in the next class. Okay. Then we have uniform and non-uniform flow. We have compressible and incompressible flow, which it depends on the density. Then we have one dimensional, then two dimensional and three dimensional flow. Then we have rotational and irrotational flow, which depends on the vorticity. Okay, so we'll discuss about these flow, and then we'll talk about a little part of Darcy's law also in the next class. Okay, till now or in week 3 lectures, do you have any questions or do you have any doubts in the week 2 lecture assignment questions? Okay, if not, then we'll stop here. I'm noting down the attendance anyway. Okay, so we'll again meet next Monday, again same time, that is 6 to 8. Okay, yeah, so if you have any questions in these lectures and all, you can ask in the next session also. Okay, so if you guys don't have any question, we'll stop here. Thank you so much for joining. Meet again on the next session. Thank you.